establish the fact that area, if it's two-dimensional, you get that factor of 2 for the alpha. Now, the next one to establish is how do you get the factor of 3? Okay, factor of 3 for volume. So let's say you have 3 dimensions. And of course, our formula we're going to derive using, if it's a cubical, or not cubical, rectangular thing, but then you can apply it to any shape, circle, sphere, any kind of 3-dimensional shape. So you have length, height, width, then you can say the volume. If the length expands, the volume final is going to be length initial plus delta L times width initial plus delta W plus height initial times delta H. So then you're going to do the product of 3 things. What you could do is you can multiply these 2 out, L initial width initial plus L initial delta W plus delta L W initial plus delta L delta W. H initial plus delta H, right? Now you can already get rid of this because remember we argued that delta L, if you multiply 2 deltas, you're gonna get alpha squared. And then that's going to be so negligible that it's not going to change anything. So we can get rid of this. Then just add these 2. So we get V final is A initial plus delta W. Remember from this we get 2 alpha A initial delta T. We already proved that from the before from the area. Now we have to multiply that by H initial delta H. Okay, now the extra step is to do this. V final is equal to A initial, H initial, and then A initial delta H, and this times this, and then this guy times this guy, plus 2 alpha A initial, H initial, delta T, okay? Plus the last one is gonna be that one. Plus 2 alpha A initial, delta H times delta T. Okay? Then you're gonna get here A initial, H initial plus A initial. Delta H is going to be 2, no, sorry, not 2. It's going to be alpha H initial delta T plus 2 alpha A initial H initial delta T plus 2 alpha A initial, and then delta H is going to be alpha H initial delta T times delta T. Oh, but then whenever we see an alpha squared, we again could ignore that. Boom, boom, that's too small. And then we focus on this, and then V final, A initial, H initial is just gonna be the area times that, so it's just gonna be volume initial. And then this one, A initial, H initial, again, volume initial. And then 2 alpha, A initial, H initial, volume initial. And then we ignore that. And then lo and behold, you get the 3 alpha. Let's see. So V final minus V initial is delta V, 3 alpha, V initial, delta T. That's kind of what they did here. Right? L plus delta L cubed and then you go all of that, and then you ignore all the ones that are too small, and then you focus on the remaining term, the 3 alpha. Right? And then you can then apply that to a sphere, let's say. If a sphere expands, right, then you can say same formula with that. So we can apply this to a certain problem. This is a good one that you could do. It's actually one of the videos that I have.
Got a small favor to ask of you. Please add your name to say you support our campaign. Okay?
Let's look here.
Okay, now we're here, we're gonna
Got
illustrate this
old
book.
school video,
We've done other
but
labs
pretty classic.
where we've shown that the object expands when you heat it up. This one is what happens when I.
Okay, so here I have a sphere. I've got a sphere, and I've got a circular ring, and it has a hole in it. So the sphere's radius is just about the same size as the hole, so it can fit there, but kind of barely. You can put it through. So then I can heat one of them here, and it's gonna expand, but they're gonna expand at different rates because one is a sphere, the other one is a ring.
Okay? What happens when I warm the bowl? What's gonna happen? Okay? So I'm gonna exert some heat to the bowl. The ball should expand, right? The volume of the ball should expand. Now the ring is kept at the same temperature. Okay? A little bit harder. Doesn't go through. Let me heat it up even more. Well, now it's even the beginning portion doesn't even go through, you see. And now it's getting even harder to go through, right? Now what happens if I also heat the ring? Is the hole gonna expand? Now what's gonna happen is it's gonna expand, right? Is the hole gonna get bigger? Because the metal is gonna get bigger, right? Does the hole get bigger or does the hole get smaller? That's often a question that's asked in physics class. When a ring gets heated up, because the material gets thicker, right? It gets thicker, 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 thicker. So does the hole get smaller or bigger? The answer is it gets bigger, okay? So if I heat this up, heat that up, okay? It can fit through, right? So a ring that is heated also gets bigger, okay? And of course, we want to get more detailed. We can calculate which one gets bigger faster, right? But if we see this, it goes through there very, very quickly. So if you ever get a ring in your finger and you can't get the ring out, you know what to do? Put it over fire. Of course. But if you heat it up just a tad bit, of course you don't have to put it over fire. You can just put something over fire and bring it, heat up your ring. It should come out of your finger, okay? And you see it got bigger and it was able to slide. The other kind of illustration of this is this. This is thermostats are based on this principle. You don't notice it here. You have a metal piece. This is made of one material. The other side is made of another material. But they're fused together, so so it's not noticeable, okay? So if I heat it up, what's happening? Why is it curving that way? Okay. Why is it curving to the left? Well, the material on the right side is a different metallic piece and it expands quicker, it expands faster. The material on the left side doesn't expand as much. So if the material on the right expands more, it tends to curve it. Now when I cool it, it's going back to normal. Okay? When I heat it, it's always going to be curving this way. If I heat it enough, I can make it wind in a circle, 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 circle. Okay? Now let me show you the basic mechanism of a thermostat. Let's say there's a switch here. Okay? Now if it cools, it starts to go up, it starts to go up. It touches the switch, right? If it touches the switch, so you say in your home, okay, when the temperature gets to 65, let's say in the winter, or 60, I want the heat to start, right? So when it gets to 60, whatever your setting is, this is gonna touch that, it's gonna set the heating signal. Okay, bring heat. When it heats, right? What's gonna happen? The thermostat is gonna heat, now it's gonna curve. After it heats a while, the heat turns off, okay? It doesn't touch the signal. Then the temperature in the room cools, cools, cools. After a while, the temperature cools, 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 cools. The thing stretches, hits the signal, the heat signal is on, so now it heats and it curves again. So that's the basic principle. You could do that also with AC, okay? You could have a signal on the other end, okay, on the bottom. And if it's too hot, if it touches that thing, AC is on this time. Yeah. So it's like, imagine this the other way, right? Imagine the other way. So that's the opposite end. Imagine it's curved this way now, right? So now, if it touches that thing, if it's too hot, it touches that thing, AC comes on. If it gets cold, it curves back down, AC turns off. So now you can kind of see the basic concept of AC, thermometer.
Nice.
It's so magically soft and comfortable.
Can I ask you a question about that?
Yeah.
So how does like the temperature, what temperature setting it, how does that like help project the metal bending? Like is like a certain.
I think the temperature setting that you're doing is only affecting this, let's say the thing is something like this. If I set it to 60, maybe it's like this. If I set it to 65, I bring it closer.
Oh, okay.
Something like that. All it is just sliding the contact point. So as it's bending, 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 like 60, you want it to bend more before triggering. 65 is just closer. So we see it as a number. It's projected to us as a number, but in the workings of the thing, it's just a distance issue. Okay, so with those, we can kind of think about, let's look at a couple of the sample questions from the test review. Sometimes I do ones very similar to those, and just to get our thought process going. We can look at test one review. So something like this one, number 2. A bimetallic strip is made of copper and steel fused together. The length of each piece is 23 at 25 Celsius, and the thickness of the copper is 0.66 and the steel 0.88. If the temperature of the strip goes from 25 to 35, what is the subtended angle of the arc that the strip makes? So, so in the test, of course, I will give you the alpha of each material. So let's say you've got 2 materials fused together. They don't necessarily have to have the same thickness. one could be, let's say, some other number, 0.88 millimeters. 0.8 millimeters, this could be 1.2 millimeters, and this could be some material, aluminum, this could be brass. And I think when I wrote the alpha, the brass was 19 times 10 to the minus 6, and the aluminum was 21 point, was it 1? When we wrote it earlier? Aluminum?
23.1.
Oh, 23.1, okay. Times 10 to the minus 6. So that means the aluminum is gonna bend like this. Let's write it like this, aluminum on the top. So let's say this top one is aluminum, this is brass. So it's gonna bend this way. So let's say initial temperature when they're straight is 20 Celsius. Then when they bend, it's gonna look like this. So I'll just write it here. And then let's say the initial length is 80 centimeters. So now what that means, they're asking for the subtended angle is that it's gonna arc like this, right? Like you saw in the video, and it's gonna make like a part of a circle. And this is theta. So it wants to know that theta. So as I heat it, it curves like this, and it makes a subtended angle like this, so it becomes part of a circle. So we could say this length here, from here to here, kind of focus on the middle of the brass. So that length is L final of the brass, right? And that's gonna equal what? L final brass is gonna equal L initial plus alpha brass L initial delta T. Right, so the change in the length is alpha brass L initial. So the final length is gonna be L initial plus alpha brass L initial. Now their L initials are the same, right? They're both 80 centimeters to begin with. So we can say, we could factor the L initial out, 80 centimeters, then 1 plus, and then alpha brass is gonna be 19 times 10 to the minus 6 delta T. Right? So based on trig, we can say alpha final, right, from trig, we can say, if you have an arc length like this, R, no, this is arc length S, R theta. So we can say S is equal to R theta, right? So this one from here to here is gonna equal the distance from, let's focus on the middle of that strip, from the middle to here. Let's call that R of the brass, the radius of the brass. So then it's gonna be equal, that length is gonna equal to the radius of the brass, the radius of the circle, the arc circle that it makes, times the angle. Right? Now let's argue the same thing for the aluminum. The aluminum center is gonna be this one from here to here in green, right? So it's gonna be LF aluminum 80, 1 plus the alpha of the aluminum, right? 23.1 times 10 to the minus 6 delta T. So what is that gonna be? Well, that's gonna be from here to here. And so from the middle of this to the middle of that is what? So basically from the middle here to the middle there. Well, the distance, if this is the width 1.2 millimeters, the whole thing, and that thing is 0.8, so the whole thing is 2 millimeters. So then it's just gonna be 1 millimeter, right? So that means it's gonna be R brass, just so that we stay everything in meters, let's just change this to meters. 0.8 meters, 0.8 meters, right? And then this one will be R brass plus 1 millimeter, we said, right? From here to here. So half of this and then half of that. So that'll be 0.001 meter. 1 millimeter changed to meter. Times theta is the same angle, right? So in other words, we're making use of the fact that they're thin. In a sense, if you think about it, this width expands also, right? And that width expands a little bit less than this width. But I'm ignoring the expansion of that width because both widths are small compared to their lengths. So I'm making the problem somewhat easier than it should be, but I'm okay in making it easier because their width is much smaller than their lengths for bimetallic strips. Very negligible widths, you know. So I'm ignoring the width expansion, but all I need to account for is the distance between the middle of this to middle of that. So that's kind of what I'm doing. So then, what do I have to solve for? So then they're gonna tell us some questions similar to there. They might say, the metal warms from 20 to some temperature. Let's say final temperature 120. So then the delta T is gonna be 100. So then we know this is 100. We know this is 100. So what are we solving for here? Well, we could solve for R brass, or we could solve for the theta. There's two unknowns, right? We could solve for whichever way we want. In that problem, they're only asking for the theta, right? But you could have also said, what is the radius of the arc that they make? Plus, what is the angle? You could ask for both, you know. So which way is algebraic the best way to solve it? You could substitute, you know what, it doesn't really matter. You could take theta, solve for it, and substitute it into here, and then solve for R first. Or you could solve for R, substitute into here, solve for theta first. It really doesn't matter. So you could say 0.8 times 1 plus 23.6. 10 to the minus 6 times 100 is 10 to the minus 4. And then R brass plus 0.001. And then theta, solve for theta from here, right? So then which is what? 0.8 times 1 plus 19 times 10 to the minus 4. Right? What's theta from here? 0.8 times 1 plus 19 times 10 to the minus 4 divided by R brass. Then what happens? The 0.8 cancels. R brass can cross multiply over there, right? This one can go over there, and then you get 1 R brass plus 23.1 times 10 to the minus 4 R brass. And then this one can multiply with this, R brass times 1 plus R brass times that plus 0.001 times that plus 0.001 times that. Then after that, just simplify that, right? So the way I did it was I solved for theta and I plugged it into this theta. And then now I'm solving for R brass. And then now this cancels. Our brass cancels, our brass cancels. Then you can subtract these two, right? 23.1 minus 19 is what? 4.1 times 10 to the minus 4, our brass. And then this plus this. Oh, this is such a small number, it doesn't affect this too much, huh? Let's see, it's 5 zeros, right? So is it 0.001, 2, and then 5. So 1, 2, 3, 4, like that. I'm doing it in my head. This plus this. Am I right? We're rusty after the winter break. Yeah, 0.001, 2 zeros. Oh, okay. Oh yeah, you're right. This is 1, 2, 3, 4. I need another 0, and then 19. Yeah. And now take this, put it here, and so for the radius that it makes. Over 4.1 times 10 to the minus 4. That's gonna give me the radius that arc makes from here to here, for the brass. Yeah. 2.44. 37 meters. That's actually a big radius. So I mean, it curves like this, and then it makes a big radius. That's 2 meters is huge. So that means it doesn't actually curve that much. It barely curves. So what was it? 80 centimeters to begin with? But then we never uses the 80, right? It canceled out. Did we ever use the fact that it's 80 centimeters long? Oh yeah, because they were both 80, it canceled out. So it's like something like this. So it's kind of bending like this visually, and then it's making a big long arc, right? And it's making a circle. Okay, now from there we can calculate the theta. So put that back into here. Then to calculate theta, you actually need the fact that they were 80 centimeters, right? So put that here, and then calculate R, put it here, and then calculate what theta is. And then the answer will come out in radians. So, .327. Yeah? 0.3279. 0.3279 rads. So I'm taking this 2.44, I'm putting it into here. 2.44397, and multiplying this plus 1 times 0.8, then dividing it by that. 3.3279 rads. Now we can change that to degrees just so we can visualize it. 180 rads is pi, pi radians is 180 degrees. So divided by pi, multiply it by 180, 18.79 degrees. Yeah, so now we can kind of say, okay, the picture looks like this. It's like this, 80 centimeters, 18 degrees. Does that mean it's really curved, or let's see, 18? That means basically, let's see, it probably looks something like this. So it goes like that, right? The bigger the radius, right? So that means that when you get down there, the angle is very, very small. 18 degrees is not too much. Now, if I keep heating it, it's gonna go like this, it's gonna go like this, and you eventually can heat it to the point where it looks something like this. That 80 centimeters goes like this, you know. So the second part of the question says, to what temperature should the strip be heated so that it curls up to the shape of a complete circle? So I could do it anything. I could heat it to the point where it looks like a perfect semicircle. I could do it so where the angle is 120. I could do whatever that I want, you know. So let's say it asks, to what temperature should you heat it so that it looks like a semicircle, right? So for semicircle, the radians will be pi radians, right? So then, in that problem, this delta t is unknown, but this time, here, you put whatever the problem is asking. You put, let's say, pi radians for semicircle, or whatever the shape you want, pi rads. So this time you still have two unknowns. Of course, this is still one of the unknowns, because as you're heating it, the radius of curvature of the circle keeps changing, you know? So this changes, this time this is changing and this is changing. So now what's the best way to solve it? Probably you probably want to just maybe substitute this R brass and then substitute it to that R brass. So something like you could say R brass is 0.8, 1 plus 19 times 10 to the minus 6 delta T over pi, right, from this top equation. And then substitute it into the bottom equation. So then you can say 0.8 times 1 plus 23.1 to the minus 6 delta T is equal to this thing, times pi. So, welcome to the spring semester, all this math already. So now distribute this in, so distribute this in. Distribute the pi in, 0.8, distribute that in. Plus pi distribution gets rid of that pi, but then multiplies by the 0.001. And then the 0.8 cancels, 0.8 cancels. Yep, that's it. So 23.1 minus 19, that's gonna be 4.1 times 10 to the minus 6 times 0.8 times delta t. It's not too bad, but you gotta make sure, get all the algebra right. And then that's gonna tell you what the delta t needs to be. And then from there you can calculate what the final temperature is, because you already know the initial temperature. Pi, because this pi from here, right, distributes in, gets rid of this, and then multiplies by this.
Okay, oh, because the question said complete circle.
Yeah, that's
Oh
a
yeah,
different
because a
one.
complete circle you would put 2 pi. Yeah. Yeah, I'm doing what if it's a semicircle. Yeah. And then from there you calculate
The
alpha.
two equations, you just made them equal to R brass and you can.
Yeah, because this one is the same. R brass, I substituted, I calculated R brass and I put it into this one. Yeah. So it's like 2 equation, 2 unknown system of equations. So let's see here. From there we get 0.001 times pi divided by 0.8 divided by 4.1. Oh, it's not that much. We only have to heat it by 957.8 Celsius. That's pretty odd. It probably will melt before that. Okay, so something like that. Something like this, for example, number 3 is a little bit different style. A glass cup of height 8 and diameter 6 is initially 25 and is completely filled with alcohol. If the temperature of the cup and the alcohol rises to 40, what happens to the alcohol? If its height goes down, what is the difference? So you basically have like a glass cup. So I'll do something different than that. So then, but slightly similar, but slightly different. So in this kind of a problem, you'll have like a cup, like a beaker type, laboratory beaker type cup. So this one is glass. Of course, you have to be given the alpha of the glass. So then the glass will expand. You can kind of think of the glass as laying it out like this. So it expands, its height goes up, and its length goes up. So then you can think about it as laying it out like this, and then closing it back up, like this. I believe I have a video on this problem too. So it's gonna end up being a bigger glass at the end. I'm exaggerating, something like that. But then the liquid inside of it, initially filled with alcohol, right? The liquid will also expand. So how do liquids expand? Well, we saw for solids that when you go from 1-dimensional to 2-dimensional to 3-dimensional, that the alpha goes to 3. And you notice that in the table, notice that in the table, when they gave, water, they gave 69 and 207. Technically speaking, I don't think they should have written water, because I believe this table is only solids. They probably meant to say ice. And then 69 is if the ice's length is much longer than either of its width or height, then that's when you can use the 69. So if it's a like solid block of ice, which is much, much longer. If the length and the width are very long, but not the thickness, then you would use twice 69. And then if it's a three-dimensional block of ice, you would use the 207, okay? But what if it's liquid water? Well, we gotta look at a different equation then. We gotta Google volumetric expansion of liquids, because for liquids, you shouldn't have any alpha, right? It should only be volume expansion. So I believe they covered that here, volume expansion. But they call it alpha V. Where is it here? I see it. They're calling it alpha V. But in a lot of other sources, they're called those beta. Okay, a lot of other websites. So we'll look here. Oh yeah, this one, we'll come back to this table, but it's usually written like. Oh yeah, they're doing they're doing here what we just did. Delta A is 2 alpha, and then delta B is 3 alpha. Okay, now for volume expansion. They never actually wrote it down, but they should have written delta V is for liquids. You should have an equation. Delta V is beta V initial delta T. And then beta is called the volume expansion. Beta is volume expansion of liquids. And then for solids, you can also have something like for gases, I mean, you can also have a constant. Delta V is beta, the initial delta T. I think the gases, they can also call them beta. But for gases, the process by which you're heating them matters. Whether it's at constant pressure or, let's see, constant pressure. No, it's constant, I believe it's constant pressure. It's the one, delta V is the volume expansion of a solid. Beta, the initial. No, that's it, yeah. It's gonna be like this, but then this is gonna be in the gas form. Gas, this is gonna be liquid. Okay, so now you can see in this table, solids, aluminum, 25, right? That's much different than the 23.1 we used. I think that one was more accurate. They say 25, but then the aluminum solid, they're calling it also beta. So there's a little bit of confusion in the way to say it. Probably they should call, if it's a solid, they should probably call alpha V. I think that would be better. For solids, they should probably do alpha L, alpha A, alpha V. Alpha A is just twice alpha L. That's the best way I would do. And then alpha V is 3 alpha L, as we showed, right? So that one is better to call it alpha V. That way we can distinguish it from a liquid. So then we can see that this is 3 times that, right? Consistently. Then when we get to the liquids, they should just call them beta. That way you can see, okay, this is immediately a liquid. So you can kind of see here, one of the things that distinguishes the liquids is that their beta is much bigger than the alpha V of the solids. Because when you're a liquid, you're already not bound to, the molecules are not bound to each other that much. So when I heat it, they should tend to expand more. You see, so 10 to the minus 6. So whereas these are numbers such as 27 times 10 to the minus 6, this is 2 more zeros, right, next to that. So it's like adding 2 more powers of 10. So we can kind of roughly say that liquids expand around 100 order of magnitude more than the equivalent solid. You see, this is about 100 times more than that. So roughly speaking, liquids expand 100-fold more. So you have petroleum, 950, glycerin, mercury, water. So now if we go 210 times 10 to the minus 6, is that the same as the alpha V of water? Actually, in one of the previous, okay, here. They're actually focusing on water right here. You see here, the change in volume is very nearly 3 alpha. This equation is usually written as delta V is beta V delta T, where beta is the coefficient volume expansion and beta is approximately 3 alpha. Note that the values of beta in table 1 are almost exactly equal to 3 alpha. With water is the weird one. Okay, so water, what happens is that the density of, they're plotting here the density of water, liquid water, at 0 Celsius, and the density of liquid water increases up to 4 Celsius. This enables life to exist in the oceans, you see? So in that plot, this is the density of liquid water. So let's say this is temperature 0 Celsius. This is what brings us back to the topic that I covered at the beginning. So the density of liquid water starts out 0.9998, I guess 85, let's say. 0.99985. Right? So the density goes up by 4 Celsius. It's almost 1. Let's just say 1 for simplicity. That's grams per cubic centimeter, right? Grams per cubic centimeter. Then it starts going down. How about if we were to extend to we freeze it to ice? What happens when you go from liquid water to ice? When you put a bunch of water in a tray of ice to make ice, what happens to the volume? Expands, right? So then what would that tend to do to the density?
Decrease it.
Huh? Increase the volume from when you go from liquid water to solid ice, you're decreasing the density but increasing the volume, right? So that if we plot the density, there's a drop in density. And ice tends to be about 90% of the density of water. Right, so the density drops. Then what happens as I cool ice? Is it gonna contract as I cool ice more? That one we don't know. I believe solid ice should behave. We would have to look that up. In other words, the solid ice, when I cool it, does it contract? Right? Most objects contract. If it contracts, what would happen to the density? It would go up again. You know, something like that. Now, the other graph we can do instead of graphing density is we can graph the volume, right? Because density is the reciprocal of volume. What's happening to the volume? Density is increasing, volume is doing what? Decreasing, right? So 4 Celsius. So volume is decreasing, and then when you're freezing ice, the volume is increasing, and I think this one, you know what? I don't know what happens on this side, let's just leave it like that. There's a jump like this. Okay, so here's what this would mean. If you start with 0 ice, okay, you transform it to water, its volume drops, right? So the ice contracts. Then if you warm it to 4 Celsius, it contracts. Then after 4, it increases. You can see. So that's why for water, the densest water is 4. And why is this helpful for life form? Because the 4 degrees Celsius water sinks to the bottom of the ocean and ensures that the ocean never freezes over. You can see. That the warmer water always goes down. And then ice always floats on top of water, right? That's why it's the least dense. And so it also ensures that the body of water doesn't freeze. Okay? They explain that in this paragraph. Water is the most important exception to the show. Water expands when increasing temperature. When it is a temperature greater than 4. However, it expands with decreasing temperature when it's 4 to 0. Water is densest as 4. If the temperature in the surface layer drops below 4, the water is less dense than the water below, thus it stays near the top. As a result, the pond surface can completely freeze over. The ice on top of the liquid water provides an insulating layer from winter's harsh exterior air temperatures. Fish and other aquatic life can survive in 4 degrees Celsius water beneath ice due to this unusual characteristic of water. It also produces circulation of water in the pond, as is necessary for a healthy ecosystem. Okay, this is a nice problem. Suppose your 60-liter steel gasoline tank is full of gas. So both the tank and the gasoline have a temperature of 15 Celsius. How much gasoline has spilled by the time they warm to 35? You see? So this kind of a problem will force you to use the solid expansion equation and the liquid together. Because you have the container that's solid, right? Do they tell us what the shape of the container is? It doesn't really say. Suppose your 60-liter, 15.9 gallon steel gasoline tank. No, not necessarily, something. It doesn't say the shape. This is the steel tank, then full of gasoline. They just give us the initial volume, right? 60 liters. So their initial temperature is given as 15 Celsius. And the final temperature is given as 35 Celsius. So it says the tank and the gasoline increase in volume, but the gasoline increases more because it's liquid, right? So liquids tend to increase about 100-fold more. But the gasoline increases more, so the amount spilled is the difference in their volume changes. The gasoline tank can be treated as solid steel. We can use the equation for volume expansion to calculate the change in volume of the gasoline and of the tank. So it says delta volume of the steel is beta of steel, which is gonna be three times the alpha of steel, right? And then for gasoline, we're just gonna use directly the volume beta of the gasoline. So the amount that they spill is the difference of their change in volume, because they start out at the same volume, right? So you're gonna get the beta of the gasoline. It's not that hard. No, this one is actually easy. Delta V spill is the delta V of the gasoline minus delta V of the steel, right? Delta V of the gasoline is gonna be beta V initial delta T minus V initial 3 alpha V times delta T. So I'm gonna use it that way so that it's a little more clearer. And then I'm just gonna factor out V initial delta T. Okay, so beta of the gasoline would be 950. Let's see where they're getting that from. Gasoline, let's see. No, it's not given. It wasn't in this table, but we could look at the other table. This is the other big table where it's all the liquids and their betas. Gasoline. You see, 0.00095. You see? So what would that be? 1, 2, 3, 4, 9.5 times 10 to the minus 4. That's the beta of gasoline. So V initial is 60 liters. Change in temperature is what? 20 Celsius. Beta is 9.5 times 10 to the minus 4. Now for the steel, we're gonna get the alpha of the steel. Well, I'll just trust it. I think it was I believe the alpha of the steel was 20. $11 to $13. Steel is 11 to 13. So 3 times that is gonna give you 33 to 39. So let's just say 33. But that is what order of magnitude? 10 to the minus 6, right? Whereas this is 10 to the minus 4. see? So then you subtract these and you multiply by, so you take this number, or if this is given to you directly, then you just take that number. But if this is given to you, you do 3 times that. You see? What did they use in this example? They used 35. What are we using?
33.
Oh yeah, it's close, yeah, 35. But they changed the 9.5 times 10 to the minus 4 to same power as that, the other one, right? So they changed it to 10 to the minus 6, so they just go 2 more zeros, and then they make this 10 to the minus 6 so it's easier. And there you go. So this amount is significant, particularly for a 60-length tank, 60-liter tank. The effect is so striking because the gasoline and the steel expand quickly. The rate of change in thermal properties is discussed in your chapters. If you try to cap the tank tightly to prevent overflow, you will find that it leaks anyway, either around the cap or by bursting the tank. Now, tightly constricting the expanding gas is equivalent to compressing it. And both liquids and solids resist being compressed with extremely large forces. To avoid rupturing rigid containers, these containers have air gaps which allow them to expand and contract without stressing them. So there's probably air gaps in the gas tank, they're saying. How would you do that? Small little holes? Wouldn't the gas leak? Just take a needle and put the holes everywhere. I don't know what they meant by that, but there's probably some gaps there that allow air to go in. They probably thought about this idea because in the summer, what if somebody completely fills the gas tank and they're both warm, and then the liquid wants to expand, where is it gonna go? And then imagine the whole thing bursts. So it's probably the important design element when you have to design a gas tank. You probably have to allow, I don't really know how they do that, the air gaps. They have to make some kind of an air gap, I guess. Okay, I like some of these questions they're giving. What pressure would be created in the gasoline tank considered in example 2? If the gasoline increases in temperature from 15 to 30 without being allowed to expand. Assume that the bulk modulus for gasoline is 1 times 10 to the 9 newtons per meter squared. So they're saying, okay, this gasoline is expanding and you're not allowing it to expand. You know, so the thing wants to just expand. So how do you define the bulk modulus? That's something that's in previous chapter in Physics 101. To solve this problem, you must use the following equation which relates a change in volume dV to pressure. dV is 1 over beta. This beta is the bulk modulus, the B. dV is 1 over B F over A times V0. We can go back to how bulk modulus is defined. The definition is dV over V. It's defined as like this: pressure divided by dV over V0. And the units of bulk modulus is pascals, units of pressure. So F over A is pressure. You see? And then dV goes down the bottom and V0 goes to the bottom, and it's just the ratio of how much volume it increases to its original volume. And then this is the pressure. So now it says here,
F over A is pressure. V0 is the original volume and B is the bulk modulus of the material. We will use the amount spilled in example 2 as the change in volume. So this is the pressure we're solving for in this case.
VV over V0 times bulk modulus.
Oh, nice problem, I like that. So this is the amount that it increased by, 1.10 liters. This was the original 60 liters, right? Times the bulk modulus. In other words, the bulk modulus tells you how much pressure do you need to increase the volume of that by a certain ratio. So then we're using the bulk modulus, 1 times 10 to the 9th.
Pascals. And then you get here
1.83 times 10 to the 7th pascals. Well, that's a lot of pressure you're creating in there.
atmospheric pressure is what? 101.3 kilopascals, which is 1.013 times 10 to the 5th pascals. This is atmospheric pressure.
This is 100 times atmospheric pressure. Wow. That's crazy. So this pressure is about 2,500 pounds per square inch, much more than a gasoline tank can handle. Whoa. Oh wow, I like this. This is one of the other things you should do as I show you different websites. I can't show you every single website that I know of in every single lecture, but there's some that I like going to, like Wikipedia. This I've used before, and I'll show you other ones as we go on. But have certain websites that kind of are like your to-go websites. Some might be for good videos that you can use. Of course, YouTube is generally a good video source, but other ones can be sources like this that have good, easy problems and some nice explanations that helps you to kind of see the usefulness of this. Like, that was really a great example that they gave of this gasoline tank. And the problem itself wasn't really hard, but just it gives you, oh, okay, I see where this is used. So you want to develop sites like that and put them on your website, not just only for this class, but also for your overall education. Sites that you go-to sites. So this one, I really like how they say here on the bottom. Another example of thermal stress is found in the mouth. Dental fillings can expand differently from tooth enamel. You see? It's like, that gave me something new perspective. I mean, I've never even thought about that. It's just like, I just saw it right now and I'm like, oh wow. It can give pain when eating ice cream or having a hot drink. Now I finally know why I have pain. All these years I've been going, and the doctor's like, don't drink hot tea and eat ice cream for 3 hours. I'm like, okay, I have no clue why, and I'm a physics teacher. Now I get it. Okay, after 50 years, cracks might occur in the filling. Oh, metal fillings, gold, silver, are being replaced by composite fillings, which have smaller coefficient expansion and are closer to those of tooth. Oh, I see. That's why we're starting to use porcelain fillings, because their expansion rate is closer to the tooth's expansion versus the gold, silver. You see all these things, that's why you gotta see how these are used, everything that you think of that we're learning, everything is being used somewhere, somehow. We're just not noticing it, or we just don't know it. Thermal stress contributes to the formation of potholes. Okay, nice. Oh, they gave you some extra problems here for practice. That's nice too. Just straightforward questions. Okay, I think that's time to maybe shift over to the specific heat capacity, and heat of fusion. So again, we define something known as specific heat. We see what its units are. We try to see what its meaning is. If it's big, what does it mean? If it's small, what does it mean? So specific heat capacity. Let's look at the top here. The specific heat capacity of a substance is the heat capacity of a sample of the substance divided by the mass of the sample. Informally, it is the amount of energy that must be added in the form of heat to 1 unit of mass of the substance in order to cause an increase of 1 unit in its temperature. So whereas in the previous section, we're learning once the temperature changes, what happens to the volume of that object or the length of that object, here we're focusing on how much energy does it take to change the temperature of the object. You see the difference? There we're saying, once we've changed the temperature of the object, what happens to its size, right? Here we're saying, how much energy does it take to change its temperature? The bigger the specific heat, the more energy it takes to change the temperature of something. You see? So the water is one of the highest specific heats. It takes 4,179.6 joules of heat to change the temperature of water by 1 degree Celsius. So if you think about it again, it's also a derivative. They go into all the article was pretty complex. Let's just go to specific. So the most basic definition would be specific heat is equal to how much heat it takes divided by the mass. So you could write it like this, 1 over n dq dt again. So it kind of looks like the definition of alpha almost. Alpha is 1 over L initial, dl dt, but then when alpha is constant, we say 1 over L initial delta L over delta t. Then it just becomes like that. So then this one is also a derivative, 1 over mass dq dt. Usually for liquids and solids, we focus on the liquids and solids. We focus on their mass, right? But for gases, we focus on what? Not the mass of the gas, but what?
Pressure.
Yeah, but more starts
Pressure.
with the letter M.
Mole.
Yeah, the moles of the gas. So for gases, we usually do 1 over the number of moles of the gas times heat over temperature. 1 over N dq dt. Not so much the mass of the gas matters, but the number of moles of the particles of gas. So this is known as molar specific heat. Molar specific heat.
This one is called, I guess you could call it mass-specific heat. Okay, so then when we say for when the specific heat is constant, then it just becomes, if C is constant over the temperature, then it becomes C is 1 over M delta Q over delta T, right? Then it becomes delta Q is equal to, this cross multiplies MC delta T. And then you have this equation, right? Delta Q is equal to MC delta T. Specific heat and heat capacity are related by mass. So the units of specific heat would be what then? Well, in this case, it'll be 1 over kilogram times joules over delta T. We could do Celsius or Kelvin over Celsius. Or you could even do 1 over grams times joules over Celsius, or you could do 1 over grams times calories over Celsius, right? The conversion between a joule and a calorie is that 1 small calorie is 4.184 joules. 1 food calorie, the food calorie is a capital C, right? 1 food calorie is 4,184 joules. So the specific heat for liquids and solids is usually written as 1 over kilogram joules or Celsius. For gases, how would it be written? 1 over moles joules over Celsius. Right? Instead of their mass, we use their number of moles. Okay, so what is the specific heat of different substances? Let's look here. I like the engineering toolbox website. That's another go-to page I go for constants. So what units is this given in? So you first look at the top and you say it's given in joules per kilogram per Celsius. But you can change it to calories per gram. So let's see what the difference is. So for specific heat of water, so let's see, the water, 4,182. But it's somewhat temperature dependent. So notice that they're saying this is at 20 Celsius. So that when they do that, that means it is slightly temperature dependent. There is some temperature dependence. So it's 4,182, and that would be what? Joules per kilogram per Celsius. Okay? So what I'm gonna do is I'm gonna just change it to the same thing as my conversion, 4,184, because more or less it's the same. So 4,184 joules per gram. So now, if we ask in the other units, what is it gonna be? If I click on calorie per gram, oh, then it's gonna give, oh, that's even better. It's gonna give both of them at the same time. 4,182.999, right? So how did it do the conversion? So let's learn how to do the conversion. From joules per kilogram, you say 4,184 joules. No, I should do 4.184 joules is 1 small calorie. 4.184 joule is 1 small calorie. And then 1 kilogram is 1,000 grams. There you go. So you convert to small calories, right? Then you convert to grams, and the kilogram cancels the kilogram, joule cancels the joule. So you essentially divide this by 4,184. And then you get 1 calorie per gram Celsius, which is what this is, right? 0.999. So there are some substances that have higher specific heats. Wow. Helium, hydrogen, 1.11. But most other substances have less specific heat than water, which means they're easier to heat or cool than water. But water is one of the hardest things to heat. So that means it's actually a good, water enables us to keep our temperature. It's a good buffer. And that's why we are able to, because most of our body is water, we're able to regulate our temperature more easily with water. You see? So other substances have, so if we go to, like, say, nickel, 0.11. Brass, 375, 0.089. Silver, 0.056, and so on. So everything is small compared to water. Okay? So now, the other concept that's also related to this is heat of fusion. Coming back to water for a second, even though for liquids and solids I said we usually measure their specific heat for per kilogram, we could also do it per mole. So there's nothing that prevents us from changing it to mole. So in other words, if I was asked, what's the molar specific heat of water? We could also find that. Molar specific heat of water. It's very rarely done, but nothing prevents you from doing that. Have you ever done that in chemistry? In your chemistry class, molar specific heat of water? So it tells us that 75.32 joules per mole per Kelvin. So how do we do it? Can we calculate that? 75.32 joules per mole. How would we do that? We should be able to get any of our specific heats from this units, and we should be able to change it to a molar specific heat just by looking at the periodic table, right? And finding out how many grams of that substance is in 1 mole of that substance. You see? So we say specific heat of water, 4,184 joules per kilogram Celsius. And then we could say 1 kilogram is 1,000 grams. And then how many grams is in 1 mole of H2O? So oxygen is, what, 16 grams? The atomic mass of oxygen. So get ready, there's gonna be some chemistry in this course as we're coming up. So 16 grams is gonna be the 1 mole of oxygen, and then H2 is gonna be 18 grams. So 18 grams per 1 mole of H2. Okay, so now divide 4,184 by 1,000, multiply by 18. And you should get 75. Deal? 4 times 18, what is that?
7.53.
Huh?
7
75.31.
Yeah.
Appreciation, guys, come on. Teacher appreciation day. I want to be like the director yesterday, the director of Parasite. He got 4 Academy Awards. First ever foreign language film. Beautiful, good film, very good film. You should watch it. Kind of a psychological thriller. Got 4 Academy Awards. Screenplay, best director, best picture, something else. He was amazing, I was like shocked. Okay, so yeah, so you see, we converted it. So now we know how to convert it to calories per gram and also convert it to moles. You just take anything and you could do times mole. Okay, now heat of fusion. Heat of fusion and vaporization. So heat of fusion is the energy needed for 1 gram of a solid to melt, right? Without any change in temperature. It's kind of weird, I don't understand why this is, but it's kind of weird that when something, these graphs, have you kind of noticed these graphs are kind of weird to understand? My students have a hard time with this too, I've noticed. When you see these graphs, what do they mean? They mean they're graphing what? They're graphing this is the temperature, I believe, and this is the amount of heat that you're putting in, right? You usually see these graphs. So as I'm putting in heat, and this is the temperature is going up. So like for water, for example, when you finally reach 0 Celsius, you have to put a certain amount of heat for it to melt, right? So let's just say you have 1 gram of ice. 1 gram of ice, you heat it. Let's say you start at -10 Celsius. So you put a certain amount of heat, then all the ice melts. Then you start putting in a certain amount of heat. No. Right? With a certain amount of heat. Technically speaking, this is wrong. I know that a student who really understands this, a person who really understands this, will immediately catch the error. What's the error? What did I do to change it? I made the slope of this graph smaller than the slope of that graph, because the specific heat of solid ice is different than the specific heat of liquid water. They're assuming if they make it the same slope, they're assuming that the specific heats are the same. Anyone know what solid ice specific heat is? It's about half of the water, I think. Specific heat of ice. You see, for ice, 2.108. For water, 4.18, right? So it's about half. It's about half of water. And then steam is even a little bit smaller than ice. So what does that mean? For water, it should take more heat to increase the temperature by a certain amount than than solid ice. And the slope of this, therefore, that means this side should be higher. You should have to put more heat. Do you see? For it to change its temperature. So the slope of this should be smaller than this by about half. This should be steeper. So then after that,
you get to steam, what should happen? It should take a lot more, so there's another error in that picture. It should take a lot more heat to boil steam. So, well, no, they got this right, but here is no good. It's too short. It usually should take a lot more energy to boil something, because what you're doing is you're taking from the liquid form and you're separating those molecules so much that you're making it a gas. Well, in order to be a gas, the molecules are not bounded to each other anymore. You have to put in so much energy to break those bonds. So this part of the graph should be larger. Then when you get to steam, what happens? Steam should be even steeper than that. Slightly steeper. Why? Because it shouldn't take that much energy. This side should be smaller for the temperature to increase. See? So then it just keeps going. Now, have you ever wondered about this graph? So what is this graph saying? As you're putting a certain amount of heat, initially some water boils, right? The rest of the heat you're putting in, that water that boils says, I want to increase my temperature. But we're saying no. All of the water has to first boil, while in the meantime, that water that has boiled, what is happening to its temperature? It can't go up. The theory says no, that water has to wait its turn. All of the water molecules first need to get free, right? Then everything together as a whole can start increasing its temperature. Does that make sense? And same thing with ice. When ice melts, part of it already turns liquid, right? And that liquid is saying, let me increase my temperature. And we're saying, no, you gotta wait your turn. All the water, the ice has to melt. It's kind of like everybody's taking a test and I have to say, if you're done with the test, just go get on your phone, turn in your test, get on your phone. You can't leave the classroom till everybody finishes. Right? I'm forcing everybody to stay in the class till all the test is over. And then the ice can increase its temperature. So is that true? Yeah? But that's what we learned. In other words, the molecule that has already turned into water cannot go up, some of my energy go to that. It has to first go into releasing everything. So maybe that's something to investigate, is why do we assume that? Why is it that the energy goes, see, the energy needed for 1 gram of water to boil, needed 1 gram of something without any change in temperature. But why can't the one that has already melted begin to increase in temperature? Isn't that weird? Okay, so now what is the heat of vaporization of water and fusion of water? This one is not just a lecture. This is a pretty good graph. Oh, I think this is a little more accurate. You see how the slope of this, they made it less than this one? That's pretty good. Oh, this one they did give it in joules per mole. Heat of vaporization of thing. Well, that's pretty good. This is the website. Well, this seems like it's a chemistry website. You see, lead in liquid goes to lead in grams. Yeah, it seems like from the way that they wrote it, it's a chemistry website. Okay, so what is the heat of fusion of water? 79.7 calories per gram. So that means if we had 1 gram of water, it would take 79.7 calories here if this was in units of heat, in units of calories. 79.7 calories to heat 1 gram of water, to melt 1 gram of ice. And then how about the vaporization? $539. Once we know the calories, we can of course always convert to the joules unit, you know. So 79.7, and then this is 539 calories. So that makes sense, right? It takes a lot more heat. It's about 6 times 80, 9 times 80, 6 times 80. Yeah, about 6 to 7 times harder. 6 to 7 times harder to boil water than to melt water. Yeah. The typical kind of problem where you will see this kind of thing going on is they're called calorimetry problems. They're not always those kind of problems, but calorimetry problems are the typical ones that utilize these kind of problems. For example, you're mixing a bunch of things, and the problem can tell you, let's say you're mixing a certain metal with water, and you're putting a little bit of steam in there even, so they can ask you what's the final temperature of the material, of the combination. Or it could give you the final temperature, but not give you one of the specific heats of the materials. And you could say, find the specific heat of that material, of that unknown material, you know. So you could just have a variety of situations. So for example, let's make up a problem. These are called calorimetry problems. So this is a typical calorimetry problem. 20 grams of ice at -15 is placed in a container of 50 grams of water at 25 and 1 gram of steam at 102. Also 100 grams of aluminum block at 80 is placed. What is the T final? So we have to kind of visualize, maybe draw something like this, like on the number line, try to visualize how many different things are placed in there. So this is 0. So we have ice here, -15. Then we have water at 25. And aluminum. And steam. doing. And then maybe draw all the phase changes that could possibly happen. So the ice has to go warm up, right? Experience a phase change, then start warming up. Probably the water might warm up. We don't know what the final temperature is, but maybe, let's say, it might be somewhere here, final temperature. Because it does take a lot of heat to bring steam down, right? You gotta bring cool steam, because the steam starts out here at 102, right? But then there's a phase change at 100, right? So you gotta bring steam down, change it, condense it all down to liquid water, and then bring it down. That's hard to do because steam, right? That's why when you put your hand in the steam, you get a really huge burn. Because for steam, to cool steam down to liquid water, 539 calories per gram. If you put your hand in steam, you get much more of a burn than in boiling water. Never do that. Never get inside of a sauna that's boiling steam. Well, of course we all do. That's why we go to sauna, right? But be careful, you know. So probably the final temperature is somewhere here. So this guy's got to go all the way there. This guy's got to go all the way there. This guy's got to go all the way there, right? And then the steam has to come down, condense, and then go all the way there, and they all meet together at the same final temperature. Okay? So what we're gonna do with these kind of problems is say the heat gained by everything that is warming must equal to the heat lost by everything that's cooling. So I think the only thing that's gonna be cooling is the heat lost by steam is gonna equal heat gained by ice plus heat gained by water plus heat gained by aluminum. So what is the heat lost by the steam? The specific heat of the steam. So I think it was in that previous page. What is the specific heat of? Specific heat of steam is 1.996 joules per gram. 1.996. Yeah, that's right. That's the steam. So, how many grams of steam do I have? Oh, that's good. I only have 1 gram of steam. So, 1 gram of steam times the specific heat of steam, 1.996. That's joules per gram Celsius. Right? Here they put kilojoules per kilogram, but it's the same thing as saying joules per gram. Kelvin or Celsius is the same because it's the difference of temperature. And the difference of temperature dT of Celsius is the same thing as Kelvin. Right? Times what? Well, we first got to bring the steam from 102 to 100. So you got to lose 2 Celsius, right? Right, so in terms of units, what's happening? This is 1 gram of steam. So now the gram and the gram cancels, right? Yeah. But then after we went down to 100, what do we have to do? Condense all that steam. So what's the heat of vaporization of steam? 530, I wrote it a minute ago. 539 calories. Oh, but now let's convert that to joules because this is in joules. 539 calorie. And then 1 calorie is how many joules? 4.184 joules, right? Times what? The mass of the steam. 1 gram. So in other words, I want to make sure that at the end, this is all in joules, and this is all in joules, or this is in calories, and this is all in calories. I got to make sure they're the same units. So this is
539, 1 calorie is these many joules, and then I multiply it by the mass. Okay? So now this is gone. Okay, then what do I have to do? Then I have to take that steam and go from 100 down to some temperature. So how much heat is the steam losing? So 1 gram, right? Well, when steam turns to water, what is its specific heat? The same as what water is, right? Which is what? 4.184 joules per gram Celsius times what's the change in temperature? You go from 100 to TF. So then it's just 100 minus TF. Why do I do 100 minus TF and not TF minus 100? Right? Because what am I doing? All the heat gains must equal all the heat losses. So I'm interested in the absolute value of the heat lost. So I gotta do positive, positive, and then here I have to do the initial temperature minus the final, not the final minus the initial. So that this comes out positive, right? So this is equal to, so all this was on the left side. Now I gotta take the heat gain by the ice. So what does the ice have to do? Go from negative 15 to 0. So how many grams of ice do I have? 20 grams. What's the specific heat of ice? Slightly more than steam, 2.108, right? Over there. 2.108. Joule per gram Celsius. Then what do I have to do to that ice? Increase its temperature by 15 Celsius, right? Times 15 Celsius. So that's the heat gained by the ice when you increase its temperature. Then I gotta take that ice and I gotta melt it. So 20 grams multiplied by what? To melt it, I gotta put how many, was it 79.7? But that was calories, so multiply it by 4.184. Right? Then what do I have to do to it? To the ice? So you gotta really visualize this. Doom, melt, then take it and all the way from 0 to TF. Right? So then I gotta take that ice, so plus, I gotta take that ice, multiply it by the specific heat of water, and what's the change in temperature? Just TF, because TF minus 0, right?
Yeah.
So it's basically, at this point, you're an accountant. You're accounting all of the heat gains, making sure you don't leave out anything. So now, how about water? Water, all I have to do is change its temperature from 25 to TF. So how much water do I have? 50. So I add to this 50 times 4.184. What's the change in temperature? TF minus what?
25.
TF minus 25. Whew. Okay, then finally what? Plus mass of the aluminum, which was what? 100. What's the specific heat of aluminum? Joules per gram, 0.9 joules per gram per Celsius. See? So 0.9, 100 times 0.9 times what? What's the change in temperature of the aluminum? TF minus 80. Okay, now multiply all this out. Good luck. And so for TF. So we have what here? Let's write it better here. 1.996 times 2 plus 539 times 4.184 plus 4.184. I'm going to distribute this into this times 100 minus 4.184 TF. 20 times 2.108 times 15. Hundred times 0.9 is 90. Right? So now collect like terms.
What are the units for,
I made sure they're all joules.
for 539?
Joules, joules,
How does the
joules.
gram-
539 is calories.
And then how does the gram?
Oh, because this is 539, it takes 539 calories of heat per gram of steam to condense the steam. So the gram and the gram cancels.
Okay.
And then calorie and calorie cancels. Yeah. I mean, yeah, calorie cancels, joules. So everything stays joules. And now collect all the terms that are numbers. Collect all these, collect all these, collect this, collect this. You know what, based on our answer, we might have to readjust it. So what I'm gonna do is I'm gonna say, let's continue this on Wednesday, and we'll come back, we'll solve it, and then we'll say, does the answer make sense? Okay, and then we'll assess. If the answer doesn't make sense, then we will adjust the answer. Okay, see you guys Wednesday.